Hi, I'm Adam. This is the Machine Tech video blog, and today I'd like to talk a little bit about centrifugal pumps. Centrifugal pumps are definitely one of the most common machines in the industrial landscape. In fact, they're second in number only to electric motors. And when you consider that electric motors are used to drive centrifugal pumps, it's safe to say that the lion's share of energy usage in the world goes towards pumping fluids with centrifugal pumps. So if you're an industrial maintenance technician, mechanic, machinist, you'll come across these machines at some point in your career, so it would do you some good to know how they work in the first place. In general, a pump is a machine which converts mechanical energy into the kinetic energy of a pumped fluid for the purpose of transporting that fluid from one point to another. But in order to be classified as a centrifugal pump, a pump needs to have two unique components. The first is a rotating disc with curved blade-like vanes on it called an impeller. And the second is a specially shaped pipe called a volute casing, which contains the impeller and the pumped fluid. In the most basic sense, here's how a centrifugal pump works. Fluid enters the pump at the center of the impeller, called the suction eye. Friction between the fluid and the surface of the rotating impeller causes the fluid to rotate. Think about it like this. Just like the friction between the road and the rubber in your tires propels your car forward, the impeller gains traction on the fluid as it spins in contact with it. The rotating fluid is thrown to the outside of the impeller by centrifugal force, a phenomenon which causes objects revolving around a center point to move away from the center. This is how the fluid picks up kinetic energy from the impeller, and this method of energy transfer by centrifugal force is why these pumps are called centrifugal pumps. The amount of energy actually added to the fluid is dependent on three factors: the density of the fluid itself, the impeller's speed of rotation, and the impeller's diameter. From the impeller, the fluid is released into the chamber of the volute casing and directed around to the discharge outlet, and ultimately into the system. Let me take a minute to set the record straight. A very common misconception is that these curved vanes help to move fluid by cupping it and pushing it through the pump. So then the correct direction of rotation for this impeller would be clockwise, right? Well, that's not really what the vanes are there for. The vane's purpose is to conduct the fluid along the smoothest possible path as it travels through the pump. Backwards curved vanes help to stabilize flow conditions at high speeds and reduce demands on the motor. The correct direction of rotation for this impeller is actually counterclockwise. And you can always tell the correct direction of rotation of an impeller just by looking at the way that the vanes are curved. It's important to add that because of the way that centrifugal pumps impart energy to fluid, the impeller must always be fully submerged and in direct contact with the pumped fluid. As we can see from this little light-duty pump, a centrifugal pump will not pump air, and it will not suck fluid through piping like a straw. So before the pump is turned on, the casing must be flooded with fluid, a process known as priming. And during operation, there must be a sufficient amount of available fluid under positive pressure at the suction inlet of the pump to replace the fluid which is being discharged. This is usually accomplished by placing the pump below the fluid level of the source tank. If the pump is ever starved of fluid, certainly the pump's performance will be affected, but it's actually more serious than that. It's possible that the pressure at the suction eye of the impeller will drop below the vapor pressure of the pumped fluid. If that happens, then the fluid will effectively boil. Little bubbles will form, travel partway through the impeller, and then collapse at supersonic speeds like little bullets, taking bits of the impeller along with it. This is a condition known as cavitation. and a pump that's experiencing cavitation is not long for this world. I know that I use these little water bubbles in my animations to illustrate the fluid path through the pump, but actually, that kind of entrained air or any other gas is the worst case scenario for a centrifugal pump. Let's talk about the volute casing. Volute refers to the shape of the casing. A volute is a geometric shape defined as a spiral with an ever-increasing radius, like a snail shell. Hopefully you'll notice that the volute chamber on this pump doesn't stay the same size all the way around. It actually increases in area closer to the discharge outlet. And at the point where the discharge outlet begins and the volute chamber sort of starts over, there's a wedge-like protrusion called the cutwater. The cutwater physically separates the discharge outlet and the volute chamber, and it ensures that fluid actually leaves the pump instead of just recirculating over and over again inside of the volute chamber. Now, the increasing area of the volute chamber is essential to the function of the pump because that's how the pump develops pressure. We've talked about how the impeller imparts kinetic energy to the pumped fluid. And when I say kinetic energy, think of it as the speed of the fluid flowing through the pump. But flow speed is only half the equation. A pump also needs to be able to develop sufficient pressure to meet the requirements of the system. Usually this involves overcoming gravity by raising fluid from a lower elevation to a higher elevation, and overcoming the resistance or friction of the pipes which conduct the fluid. Think of pressure as the ability to accomplish a task, and flow speed as how quickly the task can be accomplished. To build pressure, the pump has to do some science magic to convert kinetic energy into pressure energy. As fluid travels through the volute chamber, it actually starts to slow down as the area of the volute chamber increases. That's because flow rate, or the amount of fluid which is moved during a given length of time, is dependent on two factors. One is the speed of the fluid, and the other is the size of the chamber through which it's moving, meaning how much of the fluid is moving at that speed. If the flow rate is constant, then an increase in the size of the chamber would result in a corresponding decrease in the speed of the fluid. This is where a guy by the name of Daniel Bernoulli comes in. He discovered 300 years ago that there's an inverse relationship between a fluid's velocity, or speed, and its pressure. Meaning that if the velocity goes up, then the pressure comes down. And if the velocity goes down, then the pressure automatically goes up. So as the fluid is slowing down in the ever-expanding volute chamber, it's also picking up pressure. So that by the time the fluid reaches the discharge outlet, a great deal of its kinetic energy has been transformed into pressure energy. And I think that's a pretty amazing little trick. Well, there's your introduction to centrifugal pumps, their function, the main parts, and the basic theory of how they work. Pumps and pumping are rich and complex topics, and we'll definitely be coming back to them in later videos. But for now, that's it from the Machine Tech video blog. I hope you learned something.